Today we're gonna do some output. Output means controlling or sending data to devices external to the computer. In this case, it's 8 LEDs that we're gonna control through a simple computer program. Let me connect the LED board to the computer real quick. The place I'm connecting it to is called port C. We are gonna need that information later. As you can see, the green light comes on, which means we have power. And I'm gonna show you how this is connected real quick. Okay, this is how I wire things up. It's just 8 LEDs. Each has a resistor and they go directly to pins on the connector that goes to the computer. And there's also the little green LED, that's just to show that power is on. To actually control the electrical signals on port C, we have to use I/O registers. I/O registers are also 8 bits large, just as the CPU registers, but they have an address. But that's not an address in memory, it's an I/O address, so we won't see these registers in the machine code monitor, but we can use instructions to manipulate them. There's 2 registers that we need. The first one is the data register for port C, which is at address 009E, and it controls for an output pin whether it's low or high. Low means 0 volts connected to ground, high means 3.3 volts. And there's the DDR register. It is the data direction register for port C at 009F, and it controls whether each pin is an output or an input. So each of these registers is 8 bits wide, and each bit corresponds to one of the pins that we connected to these LEDs. So if I take bit 0 and turn it to an output high, then the LED should light up. And we can do this for each bit and each LED individually. Probably the most basic output instruction is just called out. And in this case it takes data from the A register and outputs it to a fixed I/O address. But as you can see here, the actual I/O address is not only given by the fixed value we put into the instruction, but also by the A register itself. This is mainly for historical reasons. The original Z80 only had 8-bit I/O addresses. Officially, these bits were undefined, but as it happened, it always put the A register on the address bus, the upper byte, when performing an out instruction. So now this EZ80 has 16-bit I/O addresses, and it just copies the undocumented behavior from the original Z80. So this makes this instruction less useful for us, because we have to use 00 here, because otherwise the address wouldn't be correct. So we can only use this instruction if we want to set all bits to 0, and we have 0 in the A register, which is useful sometimes, but not always. Another option is this variation of the out instruction, which takes the address from the BC register pair. As you can see, it was originally called out C in the Z80, and again the behavior that it uses, the B register for the upper 8 bits, was undocumented on the original Z80, and here it is officially using both registers to create a 16-bit address. So we could use that. We'd have to load our address into BC, and the register we take the value from, we can actually choose that. Also note that there's some more bytes here one more byte. The EasyAD can do 24-bit addresses in a special mode called the address and data long mode, but again the uppermost byte is undefined for I/O, so officially it only supports 16-bit I/O in 24-bit mode even. So I don't know what these do. Probably they are 0, or they output the, well, there's an extended byte there in 24-bit mode. I don't know what happens. It says undefined, so we are not using this mode, so it's not important here, but yeah. And there's yet another instruction called out0, which is very good for what we are going to do. As you can see, the upper byte of our 16-bit address is fixed to 0, which is perfectly fine for the addresses we have, and the lower byte of the address can be freely defined as a fixed address, and we can take the value from whatever register we like. There are also more complicated output instructions which take data from memory, and they also automatically increment or decrement the pointer in HL, which is useful if you want to output a large block of data from memory to an I/O device, but we're not going to use any of these instructions. There are many different ones, but we're going to look into these later, but not today. Okay, now let's write some code. The first thing we need to do is to set all bits on the data direction register to 0. By default they are set to 1, which means input in this case, but we want to use these pins as output. And how I'm going to do that is, first I'm going to clear the A register, which goes by using an XOR instruction on the A register and itself. So what this does, it takes each bit from these two operands and looks whether they're the same or different. And if they are different, then the result, which overrides the A register, will be 1, and if they are the same, the result will be 0. And because we're using the A register and the A register again as operand, the result will always be 0 and then stored in the A register. So now that we have cleared the A register, we can use a simple out instruction to the data direction address, which is 9F, and we take the value from the A register. In this case the out instruction works because we can afford to put the A register into the undocumented, well, now it's officially documented, upper byte, because it is 0 anyways and we need 0 there, so we can use this instruction to put the value there. And now we want to put something into the data register. Oh, I forgot, this address is in hexadecimal, of course. And now we're gonna output something to the data register, and we're gonna use the A register again to hold the value. This time we use the load instruction because it's not a simple thing like setting to 0. Load, let's say 5 in hexadecimal into there. That's a nice alternating pattern like this. 5. Oh, yeah, you can see it. That's the pattern we put into the A register, and using the out0 instruction, we're gonna output it to the address 9E, again from the A register. So you might ask now, why didn't I use LD and out0 up here? It turns out these instructions are a bit shorter in machine code, And I always try to optimize for size when I'm writing machine code by hand, because if there's less bytes to type in, there's less mistakes to make. So now let's translate this. Let me erase that real quick. Okay. I'm gonna translate this to machine code real quick. It's just looking up the opcodes and the table. Nothing really exciting. So, see you in a minute. I'm done. I've highlighted the immediate values that are encoded into the instructions, so you can see them better. As you can see here, the trick to clear the A register using XOR uses only 1 byte, whereas loading a value into there, well, it uses 1 byte more for the value, and also outputting to the using the simple out instruction, which unfortunately puts the A register into the upper byte, takes only 1 byte for the instruction and 1 for the address, whereas the out 0 instruction uses 1 byte more for the instruction. So these are a bit shorter. I'm not doing this for speed, well, it's just a few microseconds, but if I have to type less machine code, then it's easier for me. And one thing I forgot is to return from our program, so we don't crash into, well, some junk data. We need return C9. I don't have to look that up. So let's try this. Okay, I'm gonna type in the code now. AF. And by the way, this keyboard has cherry blue switches. I'm not smashing it into bits, it's just a loud keyboard. Now let's try this. So nothing happened on the screen, but if you look down to the LEDs, as you can see, we got our bit pattern showing up on the LEDs. You can compare it with what we put here, 5, There you can see the alternating bit pattern. Let's try something else, maybe F0. No, only half of them are on the left side and the right side is off. As you can see. Yeah. Okay, we can now totally control these LEDs. We can put whatever bit pattern we like onto them. Okay, for some more fun we're gonna do a little, well, kind of animation. For that we use this instruction, RLCA, and what it does, it takes basically every bit and rotates it by 1 position, so bit 7 goes into bit 0 again, bit 0 to 1, and so forth. It also puts the uppermost bit into the carry flag, but we don't need that right now. We just want to cycle the bit pattern through the register so we can have a little running LED effect. Okay, first we're gonna set everything to output again. We clear the A register and output its value to address 9F. Okay. And we're gonna start with a simple bit pattern, just 0, 1, which is just one LED, the least significant bit set. And again we're gonna output it using out 0. And we put in there the address. I'm not doing this right, am I? 9E. And now our A register. And then we're gonna change our pattern using the instruction I had. It was, oh, I forgot. Let me look it up real quick. RLCA. Okay, it's just that instruction. It uses the A register directly. Okay, and now, well, we just want to jump back to this place. So we're gonna output the new pattern, change the pattern again, and jump back. So, why did I leave space here? Well, if we use the program like that, it will be very, very fast, and we won't see any kind of animation. So we have to wait. There are better methods than what I'm gonna do now, but for a simple program like this, it's okay. We're just gonna waste CPU cycles by, well, counting down in a loop. And because we wanna count, well, kinda long, we use a 16-bit counter. 16-bit counting is also a little slower, which is good in this case because we want to wait long so we can actually see the pattern change. And what I'm going to do there is I load the BC register pair with some value. Let's say we take F, 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 so it's the largest possible value. And now we count down BC, and now we have to check if either B or C has any bits left, or if they are both 0. And if they are both 0, then we have counted all the way down. So how you do that is you load the value of the B register into the A register, and then you use the OR instruction to OR all the bits of the C register into that. So if B is 0, then A is 0 here, and only if C is also 0, the OR instruction will leave all the zeros here, otherwise one of the 1s would be ORed into that. And now I have a problem because I don't have enough space left. Well, I can erase that because the next instruction is also JR, a relative jump. So if that is not 0 yet, we're gonna jump back to the little loop. Just be careful not to jump here because, well, then you would never really count down, so I have to jump here. So this waits until it has counted down from 65,000 and whatnot, and then we jump back to the next output. Yeah. So let me just give it some structure. So here we are outputting and changing the value. This is our actual loop, and then we have some time wasting going on in between. So that's the wait algorithm. Well, just a simple busy wait counter. Okay, again I have translated the assembly listing to machine code. I have put in all the instructions, all the immediate values, and I have calculated the jumps. And if I didn't make any mistakes, we could just try this. Let's go. A, F, D, F2. Well, let's do this. Okay. The LED did just blink for a short time and then it turned off. Something has gone horribly wrong. Oops. Very stupid mistake. Our little loop here uses the A register to check the value in BC, so when we leave the loop, A will always be 0 and we have lost our pattern here. So we have to, well, adjust this. We have to use another register. And the good thing is that our 0 can use all of them. So let's use the next free one, the D register. And we have to do something different here. So there is also another instruction, I think, that's just called RLC, which can use any register, and we're gonna use the D register here. And then that should well, we also have to use the D register here, and that should fix the problem. Okay, I have fixed the code. I've changed all the instructions and I recalculated the jump because the RC instruction for the D register is 1 byte longer, but who cares? Let's try this. Ooh, nice. And I think that's about it for today. Isn't that nice? Running LEDs. Okay, I hope you enjoyed this part of bare metal computing. Next time we're gonna look into input, the opposite of output. I will also put all these videos and documentation and instructions and experiments onto the new 8.0 project website. It's not quite ready yet. I have finished all the design and now I have to write the content and link all the videos and stuff. You will see the link in the description if I'm ready with that and if I don't forget it. Until then, goodbye. Look, one of them isn't lighting up. What's wrong? Huh. Wire in the wrong place. Let me fix that. Ah, there you go.